Welcome to section 6.5 least squares problems and the very last lesson of this course. Woohoo! Sometimes inconsistent systems come up in different applications. And in these cases, if a solution is still required or demanded and there isn't a solution, the best we can do is find an x that makes ax as close to possible as b. So recall, oftentimes we represent things in this way. So what we want to do is we want to think of ax as an approximation to b. And this is where least squares problems come into play. So the semester began by solving systems of linear equations, and we introduced matrices and wrote the system in this manner here. Now, like I just mentioned, sometimes we have inconsistent systems. So what we want to do is we want to find an x that makes ax as close to b as possible. Now, in our attempt, I want you to recall that ax is in the column space of A. So because of this, we're looking for an x that makes ax the closest point in column A in B. And I know that probably sounds like, what? If you want a visual, figure 1 on page 363 may help illustrate that for you. Okay, so because we're looking for an ax as close to b as possible, what we're doing is we are trying to minimize this here. And that is the square root of a sum of squares. So that's why it is referred to as the least squares problem. So in the previous section, we know that b hat is the best approximation of b. And remember, it's just the projection of column A onto B. And, you know, what I'm about to discuss is kind of like a proof, essentially. So it's kind of the fluff that we have to go to in order to solve these problems. So if you want to fast forward, fine. So it's the last section. So if columns of A are orthogonal, then we know that we can find the projection easily by using the inner product or the dot product. So we're going to develop a general solution to the least squares problem. And we will end up with this projection again, so the hat notation. So since b hat is in column A, we know that this equation here is consistent. So we want to find an x hat in Rn such that this holds true. Okay, well, we're going to use this on the next slide. So we know that b minus ax hat is orthogonal to column A, the column space of A. So for each column, we can end up with the following conclusion. The transpose of A times b minus ax hat must equal 0, again, because of the orthogonality. So this leads to our final result. And the least squares solutions satisfy this equation. This system is called the normal equations for AB. So a solution to the normal equations is often denoted as x hat. So this all leads to theorem 13, which is stated here. Okay, so as promised, now we have the information we need in order to solve a problem. So this here is what we are going to solve in order to find our least squares solution. So let's take this first example here. It says find a least squares solution for this. Okay, so we are going to use the normal equations My kids are in Taekwondo, and whenever I see this, I say ATA, just like Taekwondo. I just thought you should know that. So first, what we want to do is we want to find ATA. And that's just the transpose of matrix A times matrix A. So remember when we transpose this matrix, these columns become the rows, and these columns become rows as well. And then we're going to multiply that by matrix A. So remember, rows times columns, and when all is said and done, we get the following matrix. Okay, so we have found ATA. The next thing we want to find is this part. So ATB, so the transpose of matrix A times matrix B, which is this guy here. And remember, rows times columns, and this gives us the matrix 10, 6. Okay, so the third thing we want to do is we actually want to solve that normal equation. So we want to solve this. So what we can do is rewrite it as a matrix equation. And you should recall from previous sections that this is the same thing as writing our augmented matrix. And then we want to row reduce that augmented matrix. And when we do, we get the following result. Oops. This is 34 over 45 and 13 over 45. So some of these answers are fractions, which isn't great, but it is what it is. So from this, we can draw our conclusion. The least squares solution is, and again, remember we represent it as x hat, is these guys here. And we are done. So that is the closest approximation of AX to B. Before I go on here, I'd like you to read through example 1 in the text. It is on page 364. It's just another example of the type that I just did, And instead of spending the time in this video illustrating another example, I thought you could simply read through it. So please take the time to do that. Now, this next example is basically the same thing that I just showed, but the matrices are significantly larger. So again, we still want to solve this equation, and we still want to break it down into pieces and find ATA and then ATB. But then once we solve the augmented matrix, it's a little bit more complicated than what we saw previously. So I'm going to kind of wave my hands a little bit just for the sake of time. If I want to find ATA, then I find the transpose of this matrix and multiply it by matrix A. And that gives me the following matrix. Cue elevator music. Similarly, when I find ATB, or the transpose of matrix A times B, I end up with the following matrix. Okay, so putting these together, I end up with the following augmented matrix. So remember, this this matrix here just becomes the final column. So that's all we do. So here it is. You still hear that music? Okay, then row reduce this. So remember, when you row reduce this, you want to find your pivots, and then once you have your pivots equal to 1, you want zeros above and below. Okay, there you have it. All right. So you can see here that this is much more complex than in the previous example. So what we're going to do is we are going to find our general solution, and then we're going to use our general solution to come up with a general least squares solution. Okay, so remember from previous lessons that, remember, this is x1, x2, x3, and x4. So my general solution becomes the following. x1 is equal to negative x4 plus 3. x2 is equal to x4 minus 5. x3 is equal to x4 minus 2, and then x4 is free. Okay, so from here, we will come up with the general least squares solution for this. So x hat is equal to, you take all the constants, so 3, negative 5, negative 2, 0, plus x4 times all of the coefficients, negative 1, 1, 1, and the free is 0. So this is the final solution. So this leads us to Theorem 14, and Theorem 14 says let A be an m by n matrix. This is shorthand for some mathematical speak, which stands for the following are equivalent. So if we have an m by n matrix, the following three items are equivalent. So those three items say that the equation ax equals b has a unique square solution for each b in Rn. The columns of A are linearly independent, and the matrix ATA is invertible. Now, remember invertible, there is a lot involved with that. You can refer to page 114 if you need a little refresher. So when these statements are true, then the least squares solution x hat is found by this here. So one way you can solve, so rather than reducing our augmented matrix, sometimes it's helpful to just jump in and find the inverse of ATA. Okay, so that example that I told you to read in the text, I believe this is what they do in that example. So the most common reason for the system to be inconsistent is that there are too many equations, and that occurs when the matrix has more rows than columns. So the last two slides I kind of thought about taking out, but it just illustrates an example from statistics and how this can be used. Because this information is not in your homework and we are not going to be assessed over it, I'm going to skip over this, but if you'd like to read through this, you are more than welcome to. Thank you so much for listening to all of my videos this term. I hope you enjoyed this last one.